Hello, welcome everybody to the second Bisq tech session. This session is going to be on Bisq's peer-to-peer network, and if you're not familiar with this series that we just started kicking off a couple of weeks ago, one second. This is the idea behind these tech sessions is to create a series of resources for both current Bisq developers and new Bisq developers that are coming along to have sort of a 1 hour session on each major technical topic inside of Bisq. Like today is how Bisq's peer-to-peer network works, and future sessions will go deep on how Bisq's overall trading protocol works, and so on. The first session that we did, you can see a link to it down below here on YouTube. That's a general technical overview. So if you're just getting started, you have no familiarity, that's the first one to watch, and then you can come and pick and choose which one you want to watch after that. And with that, I'm going to hand it over to Manfred. Just a heads up, the presentation that he's going to go through is dense, right? It's going to be a bunch of bullet points, really digging into all the particulars about the peer-to-peer network. So the way to watch this is to see, what looks like it might be of interest to you. What would you want to go deeper on? If you have questions, you can queue them up in the chat window if you're here watching it with us live, and we'll have some time at the end for Q&A. And of course, if you're watching this afterward, you can always come and chat with us in Slack about anything you see here that you want to go deeper on in the Bisq P2P channel in our Slack workspace. So without any further ado, I'll give it to Manfred.
Yeah, hello everybody. Let's just jump directly into the topic. I will make a screen sharing. Do you see my screen? Yeah, I think it should be visible. We'll cover basically a backbone of the application, the peer-to-peer network. It's quite a dense agenda for today, so I will try to get through everything in as short as possible, and then at the end we have time for discussing open questions. So first I want to give an overview about the peer-to-peer network, then talk about Tor and the aspects of Tor in the network handling, the way how the connection class is working, the different types of messages, then the bootstrapping, the seed nodes, peer management, in-memory storage and persisted storage, the threading model, and then we have time for questions. If you have a burning question, of course, just interrupt me. We can stop any moment for answering unclear, open questions. So the Bisq peer-to-peer network is an unstructured flood-fill network, a broadcast network. It's basically similar like the Bitcoin peer-to-peer network. I actually tried to mimic the Bitcoin peer-to-peer network, but due lack of good resources and documentation, and because there was quite some complexity in the way how the handling of the peers is done in the Bitcoin network, I decided to not follow it too closely, but the basic elements are similar. Bisq started with a DHT, with a distributed hash table in the very beginning, but that was dropped after a while because we never got it working in the real internet because of NAT traversal problems. And that was actually one of the main reasons why we ended up with Tor, because with using Tor and Tor hidden services with the SOX proxies, we got rid of all the NAT traversal problems and got the privacy and many other problems solved on top of this. In the Bisq peer-to-peer network, there are basically only two types of messages. There are either broadcast messages, which are public, like the offers, so everybody should and need to be able to read this, so it doesn't make sense to encrypt these messages, but they're still signed for the other. Be sure that they're really coming from this peer who has made the offer. And then there are private direct messages, like in the trade protocol. When you're dealing with the other peer, it's just a message from one peer to the other peer that's encrypted, and nobody else is part of this traffic. Yeah, we are using Tor hidden services, not Tor exit nodes, but come a little bit later about more details about Tor. Tor is not only used for the Bitcoin peer-to-peer network, which is for the whole trading protocol and everything, but also for the Bitcoin network part. That's kind of like optional. So by default, it's enabled that all the Bitcoin traffic is going over Tor as well. But in the settings, you can disable this, and then you're in the ClearNet. And an important part is that a peer-to-peer network is different, like a client-server model, of course, and you don't have, you have eventually consistency. You never have to guarantee that your message arrives at every peer, and you have to build in a lot of cautious with redundancy. It doesn't. It has very different scaling properties. The big benefit of such a network type is that it's very censorship resistant. That's probably the reason why it's used, why Satoshi has chosen it for the Bitcoin peer-to-peer network. It's and the downside is that it's not so efficient. It's not doesn't scale so well like a DHT, for instance, or like a normal client-server model. So it has its special nature, and you don't get everything at the same time. And yeah, there are always compatibility challenges. So every change we made, we have to take care to not break anything for older versions. And there are some different mechanisms in the peer-to-peer network to handle these challenges. But I'm not sure we have to go into that level of detail. Yeah, the Tor, the idea came from Bernd Brünster. At this time, he was a student. Now he has finished his study in Graz in Austria. He used basically also Tom peer-to-peer, this DHT before, and also run into problem. And then he found this solution with Tor, and to use Tor with SOX proxy as the network layer, and build on top of this your own peer-to-peer network. And yeah, he used this for a university project, and I got in touch with him and took over this idea and his library, and he's now maintaining the net layer library. And in the Bisq application, we are basically transparent to this network layer. So we only we're not aware really of Tor. We're just talking to the SOX, to the socket, and it's just one class basically, which is wiring up this SOX proxy with Tor and doing all the startup and so on, and then the rest of the network classes doesn't know anything about Tor. We are using hidden services, or onion services called now. And we are not using exit nodes. It has big benefits because the exit nodes in Tor are a little bit problematic, both from bandwidth and from their bottlenecks, but also for privacy reasons, because it can be assumed that many exit nodes are probably operated by agencies or so, as kind of like trying to get their thing into the network. And as I said before, a main benefit of this solution was to get rid of all the NAT traversal problems, so you don't have to configure anything. Like with this DHT solution, you needed to configure your router to have port forwarding enabled and all kind of stuff. And we wanted to have a setup where the user don't need to do anything and don't need to have technical skill to get the peer-to-peer network running. In the first step, when you're starting to connect to Tor, which takes usually just a few seconds, so maybe 3 to 10 seconds on average, you are starting to connect to the Tor network. From that moment on, you can receive data from. You can connect to the seed node and you can request data. But you, as node, you are not a fully connected node because you are not reachable from outside for others. For that second step, you need to publish your hidden service. That takes usually between 30 and 40 seconds. and only after that moment you are fully connected and you can be reachable over your onion address for other peers. Tor was under heavy DDoS attack the last months, which caused also quite a lot of troubles in Bisq in December, January. Luckily, that's over now. I have not followed so closely if the DDoS attack stopped or if, Tor added a lot of protections against this, and seems that helped as well. And also we see it in our monitoring that the connections are much faster, much more stable again. Before, in December, it was usually the round trip time in the monitoring to request the data from the seed node until you receive the data was taking up nearly to 1 minute or so. And now it's again something like 5 to 10 seconds, which is like it expected. But it has shown us a kind of vulnerability and dependence in Bisq with Tor. So we would be interested to get an alternative implementation with I2P. I'm not very familiar with I2P, and I think Tor has a lot of advantages. It's a much bigger community, developer community, it's much more battle tested and so on. But I2P for sure is a very interesting alternative as well. And if any developer would like to start to work on this, would be great to have a backup in case when we get troubles with Tor that we could basically run an alternative network with I2P. Can be that it's quite trivial, that it's only basically the startup process, which is different. And then we have, again, the SOX proxy, which talks to I2P instead of Tor. But I'm not really familiar with it. And yeah, an important part, which I have not added here in the slide, is that we are using the Tor binary from the Tor browser. And this binary gets started as a completely separate process. And we are talking over a TCP channel, a control channel with the Tor binary. So that's its own library, the Tor control library. So we are, it's not part of the Java space. It's really our own process, which the Bisq application is communicating over a TCP control channel with this native Tor binary, which has a huge benefit that we are always up with the latest versions of Tor. It's super efficient, it's C++. So if we would use a Java library for Tor, it would always lack some features and so on. So I'm pretty happy that we got this setup done. That's actually one setup which I have a little bit in mind also for Bitcoin, that we are running Bitcoin Core as a binary and communicate with this over RPC, and then have the benefit to have always the latest and the best version and the reference implementation of Bitcoin. But that's another topic. Back to I2P, it would be great, of course, to support both at the same time, Tor and I2P, but I assume that will be too expensive from the resource consumption and bandwidth to basically, to publish your messages all the time over both networks, and all the nodes are consuming their messages on both networks. Maybe it's possible. I fear that's too complex from all aspects, from bandwidth, resources, and dev effort. But who knows, when somebody is working on this, we can figure out if there are some ways to do it. And another topic is we should run more Tor relay nodes. SQ has started already, and I asked him that he will promote it a little bit more. Basically, I would like that we are paying for other infrastructure. For the people who are operating infrastructure nodes like seed nodes, that people who are running Tor relay nodes get paid BSQ. Of course, we cannot run thousands or so, but would be great to run at least something like 20 or whatever. A main class in the Tor peer-to-peer project is the connection class. It handles the incoming data and writes to the socket, to the network socket. We are using protobuffer for all the network data encoding. That has earlier we were using Java serialization, but that had some security risks. And a year ago or so, we moved over to protobuffer. We are very restrictive with the messages what we are accepting. So if there arrives any message which is not known in the code base, the connection will be rejected. There are some built-in kind of like DOS protection and kind of protection mechanisms in the connection class. As said, when we arrive a message which is not recognized, or when the message is too big, or anything else which is not expected. And in that area, yeah, we get backward compatibility issues. So when we're adding new messages, like now for the DAO, all the time we are getting new message types added, and all clients who have not updated then would reject the connection. And to be able to support this, there is a mechanism which is called capabilities. So you, as a node, you are telling the network which capabilities you have, which messages you know, and before you are sending, when another node sends you the data, he knows you are capable of handling those data or not. And if you are not capable of handling, for instance, new messages which are introduced in the DAO, then the other node will not send you these messages, so you don't get the problem with getting disconnected because the other node thinks that you are kind of like attacking this node with unknown messages. And important for development environment, there is an alternative not the connection class, but the network class, which is doing all the startup for the Tor infrastructure. So for local development, you can use a local host connection, and then everything is much faster, and you don't need to wait 30 seconds for having your node fully connected. Yeah, as said initially, there are different types of messages, these direct messages and the broadcast messages, basically. The direct messages are encrypted and signed, and the broadcast messages are public. And we have this flood fill mechanism. So you are sending out your messages to all the peers you know. You're usually connected to something like 8 to 12 peers. So when you're creating an offer, for instance, you are sending out the offer to the majority of those peers. And every peer who is receiving this new offer will as well send the message to their connected peers. In the details are, for having not too much traffic, there are, you as a data owner, you're sending out the message to all your peers, but when you're receiving it from another peer, when you're not the data owner, you're only sending it out, I think, to 50% of your peers. And, but to avoid that it would become an endless flooding, you'd stop to further relay messages when you have already the message. So when node A is sending the message to node B, and node B is sending the message to node C, and then node C will receive the message again from node A, it will not rebroadcast the message anymore because he has already the message. So that's a mechanism to have a kind of like a halt for the flood fill, and that it not get too much traffic. But with this flood fill mechanism, we have a high level of redundancy. So usually you are receiving a message not only once, you're receiving it a few times, which gives quite good properties in regards of censorship resistance. And it's very hard to censor nodes. So a main problem in such networks is partitioning. So when the network, for some reason, like in the bootstrap with the seed nodes, when you would have isolated islands that there are 20 nodes which are very well connected, but then there's only one connection to another island where another group of nodes are well connected, then it would be a problem, because then there is only this one connection where the messages are flowing to the other island, and when this connection get broken or get controlled, then you have an issue. But it's very difficult to attack the network in that area, to create such partitions, and I think I don't see at the moment any risk in that area. And there is another message type, the mailbox messages, which are used in the trade protocol when the other peer is offline. So after the take offer process, the other peer don't need to be online anymore. So when you are sending, I've sent the money over the bank transfer, maybe the other peer is already offline. Then first you try to send it directly, the message. when when you cannot reach the other peer, then you are sending a mailbox message, which is basically a broadcast message, but it's encrypted, and nobody can read the message. So everybody is storing this message locally, and when your trading peer goes online, he will receive the message. He will try to decrypt the message, and when he can decrypt the message, he knows the message was for him, and then he will send a remove message to the network. So every node will remove this message that we're not filling up the network. And that's a little bit a special message type, because usually all these messages have the public key included for checking the signature. That's especially important for like for the offer that you as the offer creator are the only one who can remove the offer. Nobody else can remove the offer, and that's controlled with the signature and with the public key. The mailbox message has two public keys. One is for verifying the owner. This is the sender of the message. And one is for removing the message. That's the receiver. So your trading peer who will receive the message is the only one who can remove the message. And you have, as the trader who has created the message, you're just signing the message, and it can be proven that that you are the valid owner of the message and the creator of the message. And to avoid that, every peer in the network has to try to decrypt the message, which has a little bit of cost. And at the moment, we don't have any issues there. There are usually something like 20 or 50 mailbox messages floating around. But when we would have much more users, it can be thousands or hundreds of mailbox messages, and you don't want to spend a lot of computation time on trying to decrypt all these messages. For having this optimization, we're using a prefix filter. So you only try to decrypt those messages which are matching the first bytes of your onion address, I think, or of your public key or whatever, some data which are unique to you. And then you only try to decrypt maybe something like 10% of the messages. So that gives enough privacy that you cannot say clearly that the one who has decrypted was the receiver, because with the prefix there can be many different nodes who could be the receiver of the message. It's a concept which were borrowed from Bitmessage and probably used in many other projects as well. Then some messages are stored in memory, like their offers. When you send out the offer, every node is keeping their live offers in RAM. When you're shutting down their application and you're starting up, you have basically 0 off, and you have to request it again from the seed node. And most of those messages have ownership protection, so only the owner can remove the message again. And some messages, like the offers, or most of those messages have a time to live also, that the storage doesn't get overfilled. So an offer usually can be that when you lose your network connection, or when you're killing your application without shutting down the application properly, then your offers would stay online, would dangling, and that would have the disadvantage that other peers think you're online. They try to take your offer and then have to wait until the timeout to see that you are not available. And the other disadvantage is that your storage gets flooded with too many offers over time and get clogged. So to avoid this, there is a time to live for the offers. It's something like 4 minutes. So when you lose your network connection without sending when you are shutting down your application, you are sending a remove message for all your offers. So the network gets the information that you are not online anymore and your offers have been removed. And when you go online again, you send an add message and your offers get added again. With the time to live, we have a mechanism to handle the cases where you don't do the controlled shutdown. And then we have also persistent messages. That was in the past mainly their trade statistics and their account witness data. That at the moment it's only the that the messages which only get added, so they never get removed. Trade statistics doesn't make sense to remove those messages. And with account witness, basically the same. With the DAO, we will have new messages which will be persisted and will be removed. So that has been extended now, but don't want to get into the detail of this. But it's basically data. It's similar like storage messages, but they get persisted to disk. To avoid that, you have to request too much data at the beginning. We are always shipping the current state. So with a new version of Bisq, we are shipping all the past trade statistics, persisted trade statistic data. So as a new client, you get already a lot of data. And when you are first starting up, you only request the data which is missing. So we have data handling, but maybe a little bit late on this on dedicated slide to the storage. Yeah, another bigger part is the seed nodes. As a completely new client, you don't know anything about the peer-to-peer network, so you don't know any peers. So you need to have some well-known entry points to the peer-to-peer network. Those are hard-coded in the code. You can also set it by program argument. And that's a usual concept in such networks. Also in Bitcoin, you have those seed nodes. And they are basically delivering nodes in the network, so you get known about other peers in the network and you can connect to other peers. In our case, the seed nodes have a little bit more features. That's mainly for efficiency because the Tor connection is slower in the Bitcoin peer-to-peer network. It's ClearNet, so it's much faster, much more efficient, the network. With Tor, everything is slower. We don't want the user that he has to wait 10 or 20 seconds until he is connected to other peers before he can receive any data. And for that, and also all the other peers are less reliable. So it can be that you're starting up, you get a few peers, you're trying to connect to the first peer, but then this peer is not responding or is very badly connected or just shut down before it's sending you the data, and then your startup will be delayed. So for usability reasons and efficiency reasons here, we are using the seed nodes. They're running on servers, so they're very well connected. And all the time when you're starting up, you are requesting the data like the offers from the seed node. We are using delta handling, or I come to this later with the storage. So basically, the seed node delivers you all the data, what you want to know, as soon as you are connected to the Tor network. That takes usually just a few seconds, 5 seconds or something. With that way, we can show very quickly the offer book, so you don't have to wait until your Onion service is published, which takes usually half a minute. And you can already start to browse the offer book. You cannot take an offer because you're not fully connected. Nobody could send you a message because your Onion address is not known in the network. But you can receive already data and you can play a little bit around. Then after, when your hidden service is published, you are fully connected and you are requesting again from the seed node the data, because in the meantime, it can be that you miss data. When a new offer has been published in between this half minute, you would not have received it because you are not the receiving peer in this time. So to avoid that you have missed this data, you make a second request to the seed node to have a data update, and you would receive then any data which have been published in the meantime to the peer-to-peer network. Yeah, and as I said, we're using a data handling, which is basically using the hash of the data and a map. So you are sending the seed node a map of all the hashes, what you have already, and then the seed node is only sending you the missing data items. So we are reducing traffic. Yeah, then another bigger part is the peer-to-peer management. You try to stay connected to around 8 to 12 peers, but that depends a little bit on the peer type. Also, there are different peer types, like the seed node, the direct message peer, or normal peer. And that's it's especially when you're in a trade process, you don't want to get disconnected from this peer, because when you send a message in the trade protocol, it would take more time again to start to reconnect. So you want to stay connected. So those are kind of like privileged peer. When you get too many peers, you start to disconnect peers, and you start with those peers, with the normal peers, which don't have any special relationship with you, and the direct message peers, whom you have already exchanged direct messages, like in the trade protocol, will be the last which you start to disconnect. So so there are different limits. When you have a lot of these direct peers, you will have maybe 20 or 30 peers connected, but usually it's around between 8 and 12 peers. There is this peer exchange package. As in the code, you will see all these packages which are dealing with the different aspects, like peer management, peer exchange, keep alive, get data, where you're getting the data from the seed nodes and so on. And the keep alive is to have ping and pong messages every few minutes, so that you see that which messages which nodes are still alive, and that's used also for the connection handling. When you see a connection is idle for a few minutes already, then you are disconnecting those first instead of other connections which are more active. This in-memory storage, we have different wrapper messages, like add data message or remove data message. They are packing inside them different payloads, like the offer. They have this ownership protection with signature and public key. So when anybody would send a remove data message with a foreign offer, it will fail, because you don't have the signature will fail. You don't have the private key for making the right signature. And for keeping the offers alive, we are using a refresh message. That's kind of like a lightweight message. It doesn't contain all the payload of the offer. It only contains the hash of the offer, I think, and the very minimum data which is required to have the functionality that you can basically signal the network, my offer is still alive, and please update the time to live. So I think the time to live in the offer is something like 6 minutes, and the refresh messages are sent out every 4 minutes. So usually your time to live get updated every 4 minutes, and it often never gets removed. Would be just when you're very bad connected and your messages don't get out, then after 6 minutes, when another node doesn't receive any refresh message for an offer, in 6 minutes he will remove the offer from his data map and from his offer book. And as said before, the mailbox messages are also a little bit special. They have two public keys for the sender and for the receiver. The receiver is the only one who can remove the message, and the sender is the one who is adding the message. Then there are persisted storage, where we are storing the data to disk. We are using the hash of the payload of the data as the key. We have two different types of persistence. One is more lightweight, where we try to really have the data as small as possible, because we expect that we get a lot of data, like the account witness and the trade statistics. There will be thousands or 100,000s of data items in future. And we have to take care that this data storage will not grow to 100 megabytes or gigabytes. And at the moment, I think it's something like 1 megabyte or so. But with the trade statistic, we will get an issue someday. And probably we will just not go back in history forever. And we'll only have then the trade statistic for the last 2 months or something. And then when you want more data, you request it extra from a special service. But so far, we don't have an issue with this. The same with the account witness. That's super small data, but when we have 100,000s of users, we will have hundred thousands or millions of account witness data and will sum up. So that's really designed to have very minimal data. And now with DAO, we have added new data types which require also data protection, because those other are basically protected by the hash. So the account, the account witness, it's unique by the hash. Nobody can create an item with the same hash with your data. So basically, there's no risk that your entry for the data map would be occupied by somebody else who squat your hash. And because the data are never removed, there is no requirement for having a public key in the data, which occupies quite a lot of data size. So those lightweight storage doesn't use the public keys and signatures and so on. It's really just the pure data and the hash. And these other new data items which get persisted, like the compensation requests and the votings, they will be, especially the compensation requests, you can also remove a compensation request. So there we need data protection. So, and we are not expecting that we get millions of compensation requests and vote items, so that will be more limited data amounts. So we have a little bit less strict requirements, and that's a new type of persisted data structure, which just got added a few weeks ago. And as said before, also, the old data get shipped in the binaries, so you don't have to download all the data from the seed nodes. Usually we have releases once a month. So the maximum is basically that you have to request the data, like the trade statistic data, from 1 month, which is maybe a few hundred kilobytes or so. That's not a big issue. Another important part is the threading model. As in general in Bisq, I try to avoid multi-threading as far as possible when it's not really required, because of the added complexity and risks. And we are usually mapping from a threaded context to the user thread, which is in the Bisq application, the UI thread, at the point where we are having the interface to the other layers. And in the connection class, for instance, that is where you're receiving the message. So the on message handler is doing then the mapping to the listeners. So when you want to listen to a message from a peer-to-peer network, you get your handler called on the UI thread, because the connection class is doing the mapping with doing the mapping to the user thread. So you don't have to deal with threading. But of course, in the peer-to-peer network, we have quite a lot of threading, especially the connection class has to be in a threaded context. The Tor startup code is of course also handled in threads. Persistence, writing to disk is threaded. And yes, that we're using this mapping to the user thread at the callbacks. Yeah, we have now, I think he has not joined, unfortunately. We have a new developer who will join very soon and who will focus on peer-to-peer network. He has just finished his PhD on the university in Graz as well. He is a friend of Bernd, who has done the NetLayer library, and he's specialized on security and networking, so a perfect candidate for that area. And so what are the open tasks? I mean, basically, the peer-to-peer network works very reliable and stable. The problems what we had in the past months were mainly caused by Tor. I mean, we did add a few improvements, so we added a little bit more resilience against those issues. But of course, I mean, there's a lot to improve and to increase scalability and so on. So I've added here just a few issues which are obvious for me, but there are for sure much more what we can do. I mean, the most important thing, in my opinion, at the moment is to have really good monitoring, that we are really knowing where are the weak points, where the problems. I mean, I started in December monitoring, but that's very primitive monitoring and has to be improved or changed. Yeah, to have really good monitoring to know the health and the state of the peer-to-peer network. To know, for instance, how many live nodes we have. I have a method how to check out the live nodes, but basically it's in the monitoring. It's not visible at the moment. And that's, of course, needed when we do some improvements. We need first the monitoring to see if the improvements really helped. Yeah, I mean, I'm a little bit familiar with Tor, but I'm not, by far not a specialist in Tor. Tor is a huge area, and especially with the problems in the last months, it would be really good to have more in-depth Tor know-how. So that will be a task for this role as well. And also to get more in contact with the Tor community, that they are aware of our project, to exchange more knowledge and so on. And yeah, that also we are running more Tor relays, so we are supporting the Tor networks in a greater extent. To add more DDoS protection in the connection class, there is already quite a few, but we should get more DDoS protection. There's one very interesting feature which I started to implement at the beginning, that was also an idea borrowed from Bernd, is to use a kind of like a proof of work against DDoS or against Sybil attacks, that are the costs for creating a hidden service is a time cost. So when you're starting up a node, it takes you minimum half a minute until you are fully connected. So we could use this as a kind of like a proof of work. Yeah, when somebody would like to start up thousands or millions of Sybil nodes to attack the network, it has some costs when it takes them half a minute instead of just making a connection to a network, which just takes 5 seconds. So it's a kind of like a proof of work, and it would help a little bit to add costs for such attacks. So we could use this as kind of like that you are not allowed, that you are basically prevented from a lot of features when you are not fully connected. I mean, that's already in a way implemented because you cannot send data and you cannot do a lot, but it's not really done on the network layer. So to have this deeper integrated in the network layer would be a good part. I didn't implement it as I started implementing it, but it added quite a lot of complexity, and it was hard enough to get the peer-to-peer network really stable and reliable. And at a certain point, I removed it to not lose too much time on something which was not really needed at the moment. And but yeah, it would be good to get this in at one point again. Another Another important part would be to get test frameworks. That's quite a tricky area to have really a framework for where you can test peer-to-peer networks. There are also simulation and test frameworks out. I'm not very familiar with them, and I would not overemphasize the results because they're always different, like the real network. But of course, it would help a lot, especially when starting to do optimization. It would be good to really have a tool to check if the optimization really do optimize the network, because it's very tricky. And I've seen in the past when I tried to optimize things, it turned out it was doing the opposite. It made the network more unstable. For instance, I tried to decrease a little bit the traffic by decreasing the number of users where you are relaying your message. So when you are receiving a message and you are not the data owner, you are connected to 8 peers, you're only forwarding it to 4, I think, random peers. And I played a little bit around with this number, and I think I decreased it to something like 3 or 2, and I discovered that we got more problems with lost messages that are mailbox messages, which are very important in the trade protocol. When you are sending your peer a message and the peer never received the message because the message was not well propagated, then the trade basically ends up in a dispute because the other peer never received the message that you have started the payment and opened a dispute. So it's very critical there to have really a very high redundancy and reliability, and to play around with this parameter can be very dangerous. So I have experienced that even quite trivial changes where I thought, nothing can happen, nothing can go wrong, and it was wrong. Things revert the changes. I was very conservative after this. And to have some test frameworks and monitoring would be a good precondition to start to optimize the peer-to-peer network. But there are for sure a lot of requirements for optimize it, especially from scalability. In the very beginning, I did some tests with just spinning up hundreds of nodes and hundreds of offers, and check basically if the peer-to-peer network can handle this load, because especially the offers, they are, when you have hundreds of users with hundreds of offers, every offer gets refreshed every 4 minutes, so it creates quite a lot of traffic. And this traffic, this churn can be a little bit heavy for the nodes, and the nodes can get flooded with too much traffic, and then maybe the DDoS protection get triggered when you are receiving too much messages from peers. You start to block it or to throttle it down and so on, so it can cause troubles. And there are for sure limits for the scalability. I don't think it's a big problem, because we will never have thousands or millions of offers, because offers which stick too long are serve their network. So we have to have a mechanism that offers should get taken very quickly, and we have already this with the fees, with the percentage-based fees. So when you make an offer which has a very big distance to the market price, when you create an offer with 20% distance to the market price, it will probably stick there for months and will cause just cost for the offer. For the network, because every peer has to relay all the time these offers, but nobody has really a benefit, because nobody wants to take the offer. For that reason, such an offer is very expensive, and with that we have a kind of like a disincentive for the users that they're creating such offers, and there shouldn't be thousands of such offers, because there are probably not too many users who are willing to pay a very high trading fee for that. So with that in place, when you have an offer which is close to the market price, it usually will get taken quickly, and and for that, the offer probably will not live there for weeks or for months. And for that reason, we should not really have too many offers. I will count with, even if we have really a lot of users, when we would have scaled up to something like local Bitcoin, I assume that we will have maybe 500 offers in the offer book, and maybe not really more. I mean, one way to to optimize then would be to segment the network in a way with the currencies, that usually you are only interested in a few different types of currencies. So you can basically subscribe to, you're interested in Monero or in Euro offers or in dollar offers, but you're not interested in Dash offers, for instance. And with that, we could kind of like optimize the network, that you are not get flooded from too many offers, only from those offers what you are really interested in. And as said before, with I2P would be interesting approach to see if we have a ability to add support for I2P, either as only as a backup. So when there would be really big problems with Tor, that Bisq has a kind of like a backup solution, or even better, if we could find a way to have it in parallel. Yeah, here are some references. There is some technical overview that's outdated. I wrote this when I was building the peer-to-peer network 3 years ago, basically. So, of course, there have been some changes, but the very basics are still intact. So there have not been really fundamental changes. So it gives a kind of like a rough overview, but probably this presentation now gives a better overview. And of course, the code, in the code, you will see the packages, and it's more or less structured in the way like I explained it here. And then there is this third-party library, NetLayer library, which is written in Kotlin. And this net layer library consists of several other libraries like this Tor control and SOX proxy library and so on. And yeah, we are using that library from Bernd, who is maintaining it. And basically you don't have to deal with this, but that basically delivers you all the wiring up of the Tor binary with the Tor control, with this TCP channel and so on. And we are just starting this and then get the socket out of it and talking with the socket. Yeah, I think I covered the most important parts. We are still more or less good in time, 50 minutes. Yeah, are there any questions? I mean, most of the participants have already got an introduction in the peer-to-peer network besides Bernd. So,
Manfred, there was a question by Bernard. Bernard, do you want the group chat or?
Yeah, 1 second. I read it up.
Can you hear me, guys?
Yeah. Bernard?
Yeah, okay. So
yeah, maybe I just tell the questions.
Yeah, so we've got those inbound connections and outbound connections, right?
Yeah. Mm-hmm.
So if my hidden services port is not reachable, will I receive the offers from peers?
Also, if the port is not reachable, or what is that? If the port is not reachable?
Yeah, exactly. For example, it's behind the dock.
It's the same. It's the same. Wait, let me think. So technically, it's the same connection. It's the same connection over Tor. It's not the own. It's not the new circuit. I don't remember. No, I mean the main reason why I separated it in the code was because the inbound connection is that somebody else connects you and starts the connection, and that has less importance like an outbound connection when you start or connect to somebody like in a trade protocol. So when you're in the peer management, when I start disconnecting peers because we have too many connections, we are first disconnecting their inbound connections and also for the DDoS protection because, yeah, when you get attacked or so, they are inbound connections. So there are connections where the attacker tries to make hundreds of connections to you. So those have less importance like the outbound connections, the connection what you actively are doing. So maybe they should be a little bit, yeah, it's a little bit like active and passive connections. Active are the outbounds, what you're doing. Passive are those where you get connected from outside. And the active connection have a higher priority in the peer handling. That's the main reason why they are separated, but technically they are one connection.
Okay, so if I have connected to somebody with my outbound connection, then they are going to be broadcasting stuff to me over that connection, right? They don't have to open separate connection.
No. Okay. I don't remember exactly the details now how it's handled in the code, but I think it when first you're looking up if you have it in one of the maps of the inbound or outbound, and only if you don't have it, you are adding it newly. When you get the request, you're adding it to inbound connection map. Otherwise, you are picking up the connection what you have already. As far as I remember, I'm not 100% sure. It's a while ago. Is this answered this question more or less?
Yes, thank you very much, Manfred.
Yeah, I mean, basically, usually as a developer, so you don't have a lot of contact or whatever. You don't have to deal too much with the peer-to-peer network. When you would be in the case that you have a use case which is not covered at the moment. I mean, a side note: the peer-to-peer network is intentionally designed, not general purpose like I2PF or whatever. I was looking in the time when I was looking for alternatives for a peer-to-peer network when I discovered that the DHT solution was not working. I was looking in other existing projects like I2P, not I2P, IPFS, or BitMessage I looked also closer, but at the end, none of those were really a good fit. Also BitTorrent itself, they were built with other use cases in mind, which are not our main use cases, and our important use cases like data protection was not a part of that, of those projects. Usually BitMessage had a lot of problems with the proof of work. It was really slow and had too much cost with this. And yeah, when there are some new use cases like I have at the moment with the DAO, that there are a requirement for persisting data, which are data protected, yeah, we have to add it. But basically, we have to be conservative. We have to be really sure that it's not possible to add it to existing data structures and the existing features. And yeah, but as said, it's not built with the idea to have a general purpose network where everybody can use for whatever they want to do. Of course, it can get developed in this direction at some point, but yeah, as at the moment there is no requirement. We don't have the dev resources to do extra stuff what we don't need. But I mean, as we have now the project separated in a the peer-to-peer module extracted to a project, it's even easier to make really a kind of like a self-contained library, which is not really too much related to Bisq. From the code side, it doesn't have any dependency to the Bisq domain. Also, the dependency is only to common, not to core. And in common is basically also nothing which is really nothing which is really Bisq domain relevant. So the peer-to-peer network does not basically know about Bisq. Of course, it's designed with Bisq in mind, but yeah. Any other open questions or whatever comments?
No, thanks, Manfred. So we talked already before, so it was really, but it was quite insightful. That's for sure. So.
Yeah, I would like to, in this style, more or less, I would like to continue, or maybe next week with the trade protocol, and maybe the third then with the Bitcoin part, so that we are covering the main aspects of the application on a low-level technical aspect, if that helps.
Yeah, sounds great. Thanks.
Okay. If there's not anything left, I don't know, Chris, if you have any thing to add at the end, or otherwise we maybe stop here then.
No, I'll just say thanks as well from my side. And yeah, we'll do another one of these next week, either probably Wednesday or Thursday. We can plan it out. But yeah, let's try to keep a cadence of once a week going forward. And I just want to reiterate what you were saying there a moment ago, Manfred, about the nature of P2P network and the Bisq P2P repository as it exists. It is definitely purpose-built, like you say, right? It's not intended to be a all things to all comers, kind of general purpose peer-to-peer network. It was definitely built for Bisq. But I think one of the things that makes it potentially really exciting for somebody to work on who's interested in this space, right? In the space of peer-to-peer networks, in the space of censorship-resistant peer-to-peer networks, is that it is essentially decoupled from Bisq, right? It can become that kind of standalone, increasingly general purpose for this kind of narrow set of requirements like we have. And I think that's very exciting. Like if I was a researcher, if I was somebody wanting to focus on this, I would be very interested in Bisq because, as you found out, the hardest way possible, Manfred, I mean, it literally took years, right? Going through iteration after iteration of, trying to find a suitable solution. And the simple fact was there wasn't one, right? It actually had to be invented. And I think it's something, I think you're modest about it. That's a virtue, but I think it's something to really be proud of, that Bisq has done this. And it's something that could potentially benefit many other projects in the future. And so, the sky's the limit with it, right? and you've done a good job of keeping it largely decoupled from the Bisq domain, like you said. So I just wanted to reiterate all of that for anybody watching.
Yeah, it was actually really the hardest part of the application, and also probably the most interesting or most complex. I mean, of course, the Bitcoin part as well, but with Bitcoin, it's already all there. And we're just using a library. And I think it's the biggest challenge for building a peer-to-peer application. Yeah, when you don't have a reliable, well-working peer-to-peer network, you are stuck. And there are not too many out. I mean, I2P is maybe more. In this time, 2-3 years ago, it was still much more developed. It was already kind of like prototype. It was in good shape, but I think it was not battle tested at all. And I'm not sure if it's now. And yeah, BitTorrent, of course, that's super battle tested, but that's very special purpose for large data storage stuff, but doesn't handle our use cases well. And yeah, there was not the DHT. They have quite a lot of. I'm really happy that we get rid of it, because that would have had a lot of censorship resistant problem. It's very easy to attack a DHT network with Sybil attack or Eclipse attack, and there are basically no good solutions against for protecting against this. The best solution is to make it costly, that you have to pay up with Bitcoin basically to get your node or whatever. But that's then a big barrier for entrance. And this combination with Tor to get all the privacy from Tor, that's fantastic. And I mean, maybe some people are familiar with this Tor project, RicoChat. That's a chat messaging system over Tor, which I think use a very similar concept. And basically, you could our arbitration chat system is basically the same. It's a messaging system. You send data, you send messages, even attachments to the other peer with this mailbox messages. So even when the peer is not online, he receives it. So basically, you can build a messaging application out of that what's there already. So that would not be really too hard. And we have it already integrated in Bisq, but could be a standalone application. Yeah, I'm really looking forward also that I'm really lucky that we found Florian, this new developer who will start hopefully soon. He was just finishing his work on the university and the PhD, and yeah, probably the next weeks or so he will start to get into the code and probably with the monitoring and so. And yeah, great to have really a specialist in the field there. And also would be good to get more in connection with the Tor community. I mean, I started a little bit in Leipzig at the CCC to talk with the Tor guys, and so it was very insightful. But yeah, it would be good that they are a little bit more aware of our project and maybe can help us when they see we should do some stuff different or so to whatever, to use the Tor network in a better way. Good.
Yeah, good. So let's sign off, and we'll do it again next week. Yeah.
Okay. Then thank you, everybody, and see you next week.
All right. Cheers, Tom.
Bye.
See you guys.